Every galaxy you can see in the night sky is moving away from us right now, and the farther away it is, the faster it is retreating. Some are moving so fast that they will eventually vanish from our observable universe forever. In 1998, two completely independent teams of astronomers simultaneously discovered that the universe is not just expanding, it is accelerating, getting faster every second, driven by a mysterious force that makes up about 68% of the observable universe. A bold, dramatic cinematic split shows two massive telescope arrays, one ground-based and one space-based, both measuring the expansion rate and arriving at slightly different numbers displayed as large glowing digits, with a gap between the two values labeled the Hubble tension in red, making the scientific crisis visually immediate. A cinematic first-person perspective at a large observatory telescope at night shows the eyepiece view slowly revealing a distant galaxy cluster glowing faintly against the black sky, with a light travel time overlay showing that the light left this galaxy 400 million years ago, and the observer's expression shifting from curiosity to profound realization. A cinematic historical recreation shows Edwin Hubble at the Mount Wilson Observatory in 1929, a scientist at a large telescope in a domed observatory examining photographic plates with a magnifying glass, with the famous Hooker telescope behind him and warm amber light illuminating his focused expression as he discovers the recession of galaxies. A stunning photorealistic cinematic visualization shows the James Webb Space Telescope in deep space, with golden hexagonal mirror panels reflecting the light of a distant galaxy cluster, and a data readout overlay showing the Hubble constant measurement and its uncertainty range, representing the cutting edge of modern observational cosmology. A clean, bold, animated scientific overview infographic shows the key topics including Hubble's law, the dark energy percentage, Hubble constant measurement methods, and the Hubble tension gap, all arranged clearly on a dark background and connected with a glowing logical flow. A dramatic cinematic visualization shows the Hubble tension as a crack in a cosmic map, with two measurement results displayed as glowing bars that do not meet, and the gap labeled requires new physics, becoming more visible as measurements become more precise. Welcome back to Tomorrow's Science. Let's dive in. Edwin Hubble's 1929 discovery was based on redshift, the way light from a receding galaxy is stretched to longer, redder wavelengths, similar to how the pitch of a siren changes as it moves away, and his measurements of 46 galaxies revealed a pattern that changed astronomy forever. From these measurements, Hubble derived a key relationship in observational cosmology, showing that the farther away a galaxy is, the faster it is receding, a relationship now known as Hubble's law that allows scientists to calculate distances across the observable universe. A critical point that is often misunderstood is that galaxies are not flying through space away from us. Instead, space itself is expanding, stretching the distances between galaxies in a way similar to dots on an inflating balloon moving apart without crossing the surface. The Hubble constant, written as h0, tells us how fast the universe is expanding per unit of distance, currently measured at approximately 70 kilometers per second for every megaparsec between 2 points in space. Scientists measure the Hubble constant using two fundamentally different methods. One, analyzing the ancient cosmic microwave background radiation from the early universe, and the other using nearby Cepheid variable stars and Type Ia supernovae as distance markers. The disagreement between these two methods, 67.4 versus 73 kilometers per second per megaparsec, may seem small but is statistically significant at over 5 sigma, meaning there is less than a 1 in a million chance that it is simply a measurement error. In 1998, two independent teams studying distant Type Ia supernovae, which act as standard candles of known brightness, discovered that the universe is not slowing down as expected from gravity, but is instead accelerating due to an unknown energy filling space. Dark energy, The name given to whatever is causing this acceleration makes up approximately 68% of the total energy content of the observable universe. Yet its true nature remains unknown and is one of the greatest unsolved problems in physics. The leading mathematical description of dark energy is Einstein's cosmological constant, a term he introduced in 1917 and later reconsidered, which now appears to match the observed acceleration with remarkable accuracy. Cepheid variable stars, which pulse in brightness at regular intervals, were discovered by Henrietta Swan Leavitt in 1912 to have a direct relationship between their pulsation period and their true luminosity, making them reliable tools for measuring cosmic distances. Cepheids form a key step in the cosmic distance ladder, first calibrated using nearby stars measured by parallax, then used to calibrate Type Ia supernovae, which allow measurements across billions of light years. In 2023, the James Webb Space Telescope observed Cepheid stars in distant galaxies with unprecedented clarity, confirming earlier measurements and showing that the Hubble tension is not caused by observational errors in previous data. The cosmic microwave background, first detected by Penzias and Wilson in 1965, is a faint glow of radiation filling the entire sky and represents the oldest light in the observable universe. By analyzing tiny temperature variations in this background radiation, scientists calculated the Hubble constant at 67.4 kilometers per second per megaparsec, with extremely high precision. The difference between this value and the local Cepheid measurement cannot be explained within the current standard model, suggesting either hidden errors or missing physics. One proposed solution is early dark energy, a theoretical idea that an additional energy component existed in the early universe and briefly influenced expansion before fatting. Other possibilities include modified gravity, interacting dark energy, or additional particle species, each offering a different way to explain the discrepancy. In 2024, new observations using different distance indicators suggested an intermediate value near 70, indicating the tension may be reduced but not fully resolved. If dark energy continues to drive acceleration, one theoretical scenario known as the Big Rip suggests that expansion could eventually overcome gravity at all scales, though this remains a hypothesis. Another more widely considered scenario is heat death, where the universe continues expanding, stars burn out over trillions of years, and the cosmos approaches a state of minimal usable energy. A powerful visualization shows the Hubble constant connected to key questions such as the age of the universe, the nature of dark energy, and the possible future behavior of cosmic expansion, helping scientists understand the possible future of the universe. The James Webb Space Telescope is currently conducting highly precise observations across many galaxies, aiming to refine measurements of cosmic expansion. Another independent method uses gravitational waves from merging neutron stars as standard signals, providing additional ways to measure the expansion rate. Astronomers also expect the Vera Rubin Observatory to deliver highly accurate data that may help resolve the Hubble tension or reveal new physics. The expansion of the universe is not just an equation. It means that over time the distances between galaxies increase and the observable universe gradually changes, while the laws governing these processes remain consistent and measurable. I want to hear your answer. Do you think the Hubble tension will be explained by a measurement error, or could it point toward new physics that changes our understanding of the cosmos?